Okay, so we'll get started. Um, can anyone brief like what we were seeing on the last class? What was the topic we were covering? Not able to recollect.
We discussed something about this slow corner libraries and fast corner libraries, sir, and setup and hold violations with these two things. I think some queries were also clarified. I think I remember as far as
Oh, you were not there, sir, last Sunday.
I was there, sir.
Oh, you were there. Okay, okay.
Yeah,
We talked about routing, sir.
routing, yeah, routing also to some extent.
So yeah, we were actually discussing about the static timing analysis and what is the input for doing static timing analysis, the tool that what are the inputs that the tool takes, and about setup and hold, at what level the static timing analysis is performed. All those things we were discussing in the last class. Okay, today any idea what is the session is going to work?
Floor planning.
Yeah,
Floor planning, input output.
yeah. So today we are going to do we are going to actually go for the physical design process. Like what is how is your netlist going to realized to the layout? So that is what we are going to go forward. So I hope you guys remember about the resource estimation that we did once, like taking the synthesized netlist report that we had. In the QOR report, we have seen like what is the size of my design. That is like we were estimating the resource. I hope you guys remember that. Ramya?
Yes, sir. In each and every circuit, we take that how many areas like that, sir.
The resource estimation that I was telling about, like opening the synthesized database, in that the QOR report, which says about my standard cell, total standard cell area that includes the flip flop and the logic gates, those things, like total area.
Yeah, I remember that.
Satya sir,
Yes, sir.
you are able to remember, or should I show it?
You can come back on the report once, sir. Actually, you don't need to show it just at high level. I can recollect.
Yeah, one
Very high level, just a recap.
1 minute. You are able to see my screen?
Yes, sir.
Yes, sir.
This is the QOR report, which says here about the cell count, which says like how many combinational cells are there, how many sequential cells are there. So this is a up-down counter, 4-bit up-down counter. So if it is 4-bit, then you will have 4 flip-flops. That is, it is showing, and it shows about the combinational cell count also, which is like total you have 29 combination cells, and you have some buffers, inverters, all those things added to meet the timing. So this is the total. Is being showed here. So you have the combinational area, which is the combinational cell area, is this much, and non-combinational area, which is nothing but the sequential cell area, which is this much, and buffer, inverter, all those things areas. Here, 0, and it is giving an assumption of net area, which could come up to be this much, and it is telling that the total design area will be this much. You guys able to recollect this report?
Yes, sir.
Yes, sir.
Not about others?
Yes, sir. Yes, sir.
Jayvardhan? Anirudh has joined. Anyone? Anirudh? Anirudh, you're muted.
Yes, sir.
You,
Sir, can you repeat the question? Only I've joined.
oh, now only you have joined. So I was talking about the resource estimation, as in what is the size of my chip. That for that to estimate from the synthesis report, we will come to an estimation through that. So this is the QOR report, which is quality of result report, that is part of the synthesis reports that is dumped by the tool. Here, if you see, it says about the cell count and the area that is consumed by the netlist. So total design area comes to be this much. And did I tell you? Are you guys able to recollect how do we estimate the size of the chip?
Sir, we will take square root of the total design area.
Exactly, very good. So not only that, there is some other, actually in real time that will not happen like this. So this is just a 4-bit counter, right? So it is not going to take more space. But if you see some designs which are big, those things and all, you'll not be able to give a correct estimate. So how do we estimate that? Which I have already covered. Maybe I'll just quickly do that and go into floor planning. See, whatever is the see what you have combinational cell area, okay, then you have sequential cell area, okay, other than that you have macro area, correct? So this. So what you have combinational cell area and sequential cell area, say this is the total design area that you have seen in the report. Say I assume that this is say some x micrometer square. This is the area that you have got from the report, okay, got it?
Okay.
Yes, sir.
And say you didn't have the macro area in the report, but in case you have macros, in case you have SRAMs and all in your design, say that is some like y micrometer square. So how will you do a resource estimation? That is what is the task now, resource estimation. Resource estimation basically means what? What is my size of the chip? My size of the chip that I'm going to fabricate. Okay. So now I have x micrometer square and micrometer square and y micrometer square. Now what I will do is I will have to multiply this with 1.2, a factor of 1.2, and multiply this with a factor of 1.5. This is what I was asking, whether you are able to recollect. So now say the answer is again I would say like x1 micrometer square and you have y1 micrometer square. Why I do for 1 point multiply by 1.2 and 1.5? Any answer?
Sir, wiring or
Wiring, sir.
Yeah, for doing routing, I will have to need that which is not a counter at synthesis. So now I will add this, say x1 plus y1. So this micrometer square is my area of my chip. So what says plus x1 plus y4 cross 4. Okay, 4 micrometers cross 4 micrometer. Now in today's class we will start with floor planning and IO ring. Okay, so before going to floor plan, let's start with IO ring. Okay, why do you have to do what is an IO ring basically? IO ring is nothing but your chips, whatever the chip you are going to design, that through IO ring only, through IO only it is going to communicate inside, and whatever is the data inside the chip, that is going to send it out outside. Okay, so how does the IO ring looks like? So if this is the 4x4, okay, and your IO pads will be something like this. It will be got it. So this is your IO pads, which is going to comprise of all the functional. These pads are going to comprise of functional and power pads. It will have functional pads and power pads. So functional pads is nothing but your design, whatever the input and output pads are, right? Those are functional pads. Power pads are the IO pad, are the IO pads, that is the VDD and VSS pads, for which is going to supply the power to this to the core area, this area where your actual cells are going to standard cells and macros are going to sit, and as well as you will have IO VDD and IO VSS pads. IO VDD, IO VSS pads are going to supply power for the 1 minute. That is, this is the IOs entire for the entire IOs. For the entire IOs, the IO VDD and IO VSS pads are going to give power, so that the pad gets powered and allow the functional inputs and outputs to send the inputs and outputs. Okay, so what all things it comprises of? It basically say in this design, these two are my IO VDD, IO VSS. Say these two are my again say my core VDD and core VSS. So core VDD, core VSS is going to supply power to my core area. Okay, let me, for the ease of understanding, let me say this is my core VDD and core VSS. So this is my IO VDD, IO VSS. Okay, so what this core VDD, core VSS parts will do, it will go and supply the power to my core area, which is inside the data. So how are we going to supply power? So there will be power strips, power ring strips that we will try to distribute it like this. We'll have power strips, VDD, VSS strips here. These strips are getting connected to this pads, VDD, VSS pads, and from this power strips, there will be supply going inside the chip. Inside the core area. So these are the role of this VDD VSS pads role is to supply power to the core area, to the actual logic area, and you have IO VDD, IO VSS to give supply to the all the IO pads, and remaining pads are functional pads, which is like which is going to facilitate my design requirement. Like if you have the inputs, whatever is the design input, those input pads will be there. So other than that, you will have inputs and output pads. Okay. So what all the whatever we have seen now, let's list it out. What are the types of pad cells you have now? Types of pad cells. Yeah. Can you say what are the types? Looking at whatever I have said now, can you list it out? What are the types?
Functional.
Yeah. So functional pads will be something as input pads, and you have output pads.
So,
Correct?
so those in the diagram, those will be existing along with this VDD-VSS and IO-VSS, right? The
Those,
diagram.
which will be?
The functional pads,
Yeah, these
right?
are functional pads. Say these are functional pads.
These are functional pads.
Yeah.
Okay.
I'm just giving
Other-
as an example, but in real time it will not be in this pattern. It will be
Yeah,
on
yeah.
its own.
Just for us to visualize. Yeah, yeah.
Just for you to understand the
Yeah.
variety of pads, I'm putting
Yeah.
it. Okay.
Okay.
So you have input pads, output pads. Okay. Then you have I/O pads, which are bidirectional pads. Okay. These are meant. All the first three is meant for functional. Then you have, what is this left?
Power pads or core pads.
Power
Yeah,
pads.
power pads. So it's also called analog pads. So these analog pads are pads that are specifically meant for some analog. Then these analog pads also will come into picture. So these are the grossly different types of pad cells that is there. Okay.
So you are saying like IO is also part of this VDD-VSS, right? So the third one is part of fourth one is what you're saying. No,
Which one is third one?
no, the VDD-VSS also contains the IO pads also, right?
Yeah, that's what pad for VDD-VSS includes IO-VDD-IO-VSS.
Okay. So the third one is separate, right? The third one is also.
Third one is a bidirectional pad. Bidirectional pad means that pad can behave as an input pad or it can behave as an output pad. So these are some bidirectional pads are like it is part of design requirement. For example, in some designs where on one particular pin they wanted to keep it as bidirectional, right? At some point of time that pin will behave like input, and at some point of time it will behave like.
Okay. Okay.
See, you don't say it as IO pads. You say it as
Okay.
bidirectional pad.
Bidirectional pads. Okay, so that was confusing. Thank you.
Okay, bidirectional pad is going to be a functional pad that will act functionality. Say in your I2C, you heard of I2C? I2C is a protocol, okay, which has SDA and SCL as the pin. These has two pin, SDA data pin and SCL the clock pin. So sometimes this data pin for this peripheral, this act sometimes as input and sometimes it will act as output. That means what? Internally they will control the register. So whenever this SDA has to act as input, that means it will from the pad. So here SDA will act as input pad at that time. And when SDA is configured to be as output, that means through SDA there will be data coming out. Okay, so there are peripherals which will need bidirectional pads.
Okay, then how we decide in a particular pin which can act as a which connected to the bidirectional pin like that?
It will be told to you. You will be given. What about the packaging? Can you
Like,
give-
yes, sir. How does the packaging interface with these pads, sir? Like IO pads and so on?
Yeah. So we have something called as a bond pad. Okay. Now, when you are going to do packaging, packaging is going to come above this. And these are my packaging pins. Okay. Now, this bond from this bond pad, it will get connected. I mean, the packaging team will connect the packaging pin. This pin is outside the package. So inside the package, there will be a place called lead. Package lead will be there. So from this bond pad, it will get connected to the lead here. So to the lead, the connection will be there. And henceforth, you will have the connected package there. That's all. Anything else you wanted to explain in this?
Yes, sir. About the geometry of the bond pad, sir. It will affect the resistance value of the pad itself.
Geometry of the resistance. I didn't get your connect. I mean, it's not getting connected to me.
Yes, sir. The signal, the waveform of the signal, it will change due to the bond pad itself.
No, it will not change. Why it is going to change? See, bond pads are not going to. It is not going to affect anything about your signal. This bond pad is going. It is a place where the connectivity is done between the package and your die. So what are you saying?
Nothing, sir. I got it clear.
Yeah. So
I had a misunderstanding.
yeah. It has nothing to do with the signal. It is just to get connections only. Okay.
Yes, sir.
Okay. So you are able to see my screen.
Yes, sir.
Okay. So so this is a netlist for the RISC-V core. That is the Shakti RISC-V core. Okay. So I have done the synthesis here. So this is the report. Okay. I think with this report only we were doing the resource estimation last time. So Q over is here. So here the design area is this much micrometer square. So all inputs outputs to the IO pads, okay, to the IO pads, and decide the and do the IO ring planning. Okay. So I1, I2, I3, output is your O1, O2, O3. Now then you will have your logic always at the rate of offset of clock. So you have clock also is your input. Then you write your design, okay, then you do end module. So once you take this RTL and do synthesis and get the netlist, so your netlist will also have the same thing. You have module inputs and outputs, okay. Now if you're going to take this and make it as a full chip, so first step is doing the IO plan. Then you instantiate all the pads, all the IO pads, your functional pads, and your and the power pads. Okay, so this estimation of the power pad, how much functional pads you have, with respect to that, you will have to allocate the IO VDD, IO VSS pads, and how much the current that is going to get drawn by your core VDD, core part, which is going to be your logic part, how much power it is going to consume. With respect to that, you will have to allocate the number of core VDD and core VSS pads. Any doubt until now? Is it confusing? Is it not clear?
Yes, sir.
Okay. So now I'm going to tell you like.
Sir, one doubt. So while deciding how the chip formation, based on what we decide, how many VDD pads, how many VSS pads we need to provide for that chip?
Basically, it will be estimated by the amount of power that is being consumed inside the, how much is the logic power it is being going to consume. To that we will estimate and distribute the VDD VSS pads accordingly.
So this will be part of this IO ring step, right?
Yes.
So do we first first we estimate within what area this chip should first be in, and then surrounding that area you first put the IO pads, right?
Correct.
And
so where will be your question is where will I get the power, correct?
Yeah, so some chips will have multiple VDD pads, multiple VSS pads, and then some chips have some 3.3 volt as well as 1.5 volt pads, different voltage pads and all that.
Yes,
So
yes.
based on what we decide, how many pads should we allocate for this level of voltage supply, and how many pads should we give for this voltage supply, and so on.
Okay, so depending upon now, if your core logic, if your chip is there, and this logic will comprise of different elements, different blocks. Say this is your FPU inside the chip, and this is your another block, say B2, and you have another block in this chip which is B3, which has SRAMs macros inside this. So if they are saying this B3 is going to work accordingly, we will have to place the number of VDD VSS pads for both the part of the design. Now, say for I will have to put say 2 pair of VDD VSS, which is going to supply to put 4 pair of VDD VSS supply, which is going to supply 1.1 volt. Through this, I will decide. Is it clear, one?
Yes, sir.
Okay. Now let's assume for simplicity of understanding, let's assume we have only one domain, one power domain. Okay. Now, yeah, someone else is having doubt, Ramya.
Sorry, sir. Why, sir, one thing. What do you mean 2 pair, 4 pair means?
Pair means one pair is one VDD VSS is called one pair.
Yeah.
So now for the simplicity of understanding, let's consider you have only one power domain. Okay. And your chip is going to say is going of the supply. Only I have said this particular of formation. Like if you see here, I have taken taken this VDD VSS, okay, this VDD VSS, and this VDD VSS I have connected to the inside ring, okay, I have drawn a ring, that is the metal strip there, okay. From this metal strip, I'm going to supply it to the core, okay. Not only I will have a pair of VDD VSS here, I will have it one more here, VDD VSS, and I will also have, this is whatever I'm saying is a separate topic by itself. It's called power planning. How do you do a power planning inside the chip? Okay, so this is a separate topic by itself. We will come to that. Okay. Now today's session is going to be this IO ring. I hope I have said a little bit about that. More detail, yeah, I will say. Yeah, tell me, sir.
So the pink one, that ring, that is the IO ring, sir, the pink.
No, not the pink one. Pink one is not the IO ring. Wait, I'll draw it. This one.
Okay. That close to the core one, actually.
Yeah, there's the between the core and the IO ring.
IO ring.
Yeah.
Yeah, the pink one, what is that called, sir?
To power the IOs. Okay. So through IO VDD, IO VSS, you are going to supply power to all the IO pads.
Right.
So yeah. Okay. So there is a few more. One is say you have your chip. Sorry, you have your die and the pads. Okay, now I have the one which is marked in red. Okay, the one that is marked in red. The one that is marked in red is, you can assume it as my core VDD and core VSS. And that is okay. So about this only your packaging is going to happen. Okay, so these are my package pins that is going to come out of the chip. Okay, so now my pads are going to get connected to my the packaging pins. Okay, now what usually the packaging and all will have features, like it will have extra features. Like you have, see, if you see that here you have 4 pair of VDD VSS. Okay, correct? 4. So how many are able to see, like how many pairs of IO VDD IO VSS are there?
Oh, sir. IO VDD, IO VSS.
Yeah, IO VDD IO VSS.
Sorry, four are there. Left side and right also there. Yeah.
No, the red one is my core VDD core VSS. Blue one is my IO VDD IO VSS. So totally how many core VDD core VSS is there? IO VDD IO VSS is there.
4 core VDD VSS and 4 IO VDD.
4 pairs of
Yes,
IO VDD.
both.
Yeah. So what will happen is in your packaging there will be something like this. Okay, there will be 2 separate planes for my core VDD core VSS and IO VDD IO VSS, which gets connected to one particular pin like this. Okay, so what will happen is all my core VDD core VSS will get core VDD core VSS. Okay, it will get connected to like this and come out here. And come out here as core VDD and core VSS. So instead of connecting each pad to each pin of the package, there will be separate planes for power. There will be separate planes for power. So this is called power planes in the package, which will short all the power pads, all the core VDD core VSS pads, and bring it out as one pair outside the package. Instead, if suppose this power plane is not there, that means what we have to do is we have to connect each. We have to bring, instead of this, you will have to connect each outside. Like all the 4 pairs has to be brought outside like this, something like this. Got it? So this will save the number of pins. This power planes will save the number of pins. Is it clear?
Yes, sir. So 2 power planes are there.
1 minute, Satya. Yes, Mita?
So usually these power planes would be always there in the chip, right?
The power planes will be there inside the package. This is about package I'm talking. I'm not talking about.
Oh, yeah, sorry. About the power planes will be there, right? You said that it won't be there, and then you will have to bring it out. So
Yeah.
are there some variations also in such cases?
Yeah. We will have sometimes power planes facility will not be there as part of package. Then we will have to consider and bring every parts outside only. Yeah, Satya, you were saying something.
So we have 2 power planes, right, sir? Here.
Yeah, we have power plane which takes care of the core VDD and core VSS. Similarly, you will have separate power plane which I haven't drawn. Similarly, you will have separate power plane that will take care for IO VDD and IO VSS and brings it out. Say here it brings it out as IO VDD and IO VSS. Okay, and it gets connected. Say here it is there.
So overall, we are kind of aggregating those things and connecting it to the power plane, right?
Exactly. This is
Just
for actually to say in order to not to use all the pads inside all the IO pads, you need not bring it out. Rather, it will get the number of pins, it will get reduced. The package pin will get reduced.
Okay. So what is the criteria? Like, the power plane can accommodate this many number of pairs of core IDD or IO IDD. It can accommodate any number of pairs, or is there any limit, or what is the criteria?
Yeah, that will be part of your package document. There will be package document that will be given to you. In the package documentation, it will be told everything.
Okay.
It is specific to the package. Yeah.
Okay.
Okay, so this I wanted to stress upon here. Now, the main context of the crux of this class is not all this. The crux of the class is this one: types of part cells. Okay, what are the types of parts, and basically what is the role of your IO pads, and how do you structure it? How do you plan and place it? Okay, so once you have done your IO ring planning, now you are going for the next step, which is the floor planning. Floor planning, the IO ring planning is also part of floor planning only, but I have handled it separately. Now I'm going to talk about this area, which is I have marked inside, right? This one we are going to do floor planning in the core area floor planning, which I'm going to talk about. Okay, so what is it? What is it floor planning is? Just give me 1 minute. I'll just have some water. Yeah, so I'll just show you one sample IO ring layout, okay, so that it stays inside your mind, it doesn't vanish away. You're able to see my screen?
Yes, sir.
Yeah. So this is something. These are the IO pads, which is here. You're able to see, right? This is one pad. This is the second. Say this is first pad, second pad, third pad, the green ones, fourth pad, fifth pad, sixth, seventh, eighth. Okay. And the violet color you see, right? These are the bond pads for each IO pad. These are the bond pad that is going to get connected to the package lead pin. To the package it is going to get connected. Okay. Yeah. This is a image that I wanted to show you. And so what is that is left? Okay, that's all. We will see when there is hands-on, right? At that time, we will see more details. Any questions until now? Okay. Okay. So what are we going to do now is for floor planning, we are going to plan where all the macros are going to sit in my design, all those things. Okay. So a little bit. So what are we actually right now we are doing physical design. Physical design. So what is now actual physical design definition actually comes now only where physical design is the process. Okay, it is a process of transforming your netlist, that is a synthesized netlist, into layout.
So you're writing somewhere, it's not shared.
Oh, I'm sorry. I was writing. You're able to see now?
Yes, sir.
Yeah, please. Yeah, whenever I missed it, please remind me. Thanks for that. Okay. So what is it? What is the physical design? Physical design is the process of transforming your netlist into the layout, which is called GDS. Okay, which can be manufactured. Okay. Now, there are certain terms which are referring to this. Like it is often referred as PNR, which is place and route, or as APR. APR is nothing but automatic place and route. Okay, so what are we going to do in the process of physical design is you will have to meet the design slash technology, or whichever technology you are targeting. You have to meet the design slash technology constraints and optimize for area, power, and timing. See, this is a what do you say, before going to floor plan, I'm just giving few insights. What is now your netlist is going to get transformed to. How are we going to approach after this? Okay, so for that only I'm just giving a pre-insight. Okay, now you are so what are the approach of your, there are two approaches will be there for to take your netlist. Okay, one is the flat PNR, which we'll do, or you have hierarchical PNR. Flat PNR is like you have your example, right? We did an up-down counter. Up-down counter is a very small design. Okay. Similarly, you have your design, which is like one flat netlist that is not going to have any blocks inside that. That is called a flat netlist, and we will do flat PNR. So flat PNR nowadays nobody does. Okay, because you don't have an option of doing flat PNR because increasing design size and complexity. Okay. Hierarchical PNR is preferred now, is the one that is being taken consideration now. This hierarchical PNR is say it is a technique called like divide and conquer. To deal with huge design sizes and complex designs. Okay, so now we will always talk about hierarchical PNR. Okay, so now as a first step in physical design is the floor planning. Okay, then if after doing floor plan you have placement, then you have CTS, then you have routing, then you have after routing you will go for sign off. Okay, in this we will start with floor planning. Okay, in floor planning what you will do, you will import the synthesized netlist into this step. Okay, that is the first thing. You import the netlist. Okay, so what is floor planning is about? Floor planning is about fitting given logic in a target area with timing, power, design / technology constraints. Okay, so so we have already estimated the area size, the chip size, right? So we have now the boundary to play. We have the ground and we have the boundary to play. Within that only we are going to play. How are we going to construct my design there in that boundary is being taken care by this first step itself, the floor planning. Okay, so this step is going to be a very critical step because it is going to be a very critical step because it has lot of bearing on the subsequent steps. Okay, see, I have just put up a statement here saying that it has a lot of bearing on the subsequent steps, but in the actual real time, if you do a bad floor planning, that means you will not realize it at that time. Instead, you will go through this entire all this process and you come to until routing. At routing only, you will see that I'm not able to meet timing, and that is something because of my bad floor planning. Because my floor planning was not done with all due intelligence. Because of that only, I'm not able to close my design. So that is something going to take hell lot of amount of time, because once you start from floor planning and reach routing, it takes more than 2 months for this to get completed. Okay, and after 2 months in the project you realize that it is not meeting the timing, and that is because of this particular floor plan issue. Then you are going to change the floor plan again and again, take the design and flow through all the steps. That is something a very, very bad project planning and very bad decision. So you will have to do very intelligently. You have to do floor planning and see where you are going to place your blocks, where are you going to place your macros, everything you should have fingertip, and then only you have to go for floor planning. Okay, so floor planning will also, if you are doing a bad floor plan will also lead to blow up in power, timing closure, and because of this, what can happen? It can overall increase in development cost. Okay, which is the factor. Okay, development cost and per unit cost of the chip. Okay, yeah. To impact the entire physical design process, if you have chosen a floor plan, a bad floor plan. Okay, this entire process of identifying this. Okay, this process of identifying that whether you have done a bad floor plan or not will take nearly 2 to 3 months. Any doubts?
So are there any methodologies we follow for implementing a floor plan based on this?
Exactly. Yeah, that's what I'm going to say about after that. After this, I'm going to say that only.
Sir, I'm seeing a blank screen now. Is it the issue with me or I don't know?
No, I think everybody is able to see my whatever I'm writing it out. Everybody is able to see it.
Okay.
Yes, sir.
Maybe it's a network issue from my end. Okay,
Yeah, I
thanks.
think you can go out and come again in Satya sir.
Yeah, I logged out and logged in again.
Okay.
Still I'm trying actually. What was the issue? Okay, fine, sir. I will see.
Fine, I'm proceeding.
Right, sir.
Yeah. So basically, how this floor plan gets more accurate is like it is just like a chicken and egg problem only. Okay. So you will have details. Okay, you will have all the details that is needed for accurate floor plan. Okay. Yet you will have all details needed for accurate floor plan, but yet you will have to go. You will have to basically get your floor plan. Basically, you will have to go iterations. Your floor plan will go iterations, and you will arrive to one particular. You will reach to one particular floor plan with all due understanding of the design. Okay. So what are the key to have good floor planning in your design? Okay. Let me say this way: keys to good floor planning. of full chip. Okay. Okay. First important step. Okay. First important step is you should have basic design and know that you have it. If the designer gives you this basic understanding that your design will have these many number of flip-flops, your design will have these many number of macros, and these macros are part of this module inside the design. These macros are like, these are the various varieties of macros that is there. Varieties means, say you have 64 cross 32 macro, there are 4 number of such macros. Then you have, say, 128 cross 32, you have 2 number of macros. Say you have 128 cross 128, you have 4 number of macros. Like this, you will should have basic design understanding, like what is it, like which all modules are there, how are they connected to all these things has to be which you should have that understanding. This understanding will be given by the